The Basic Principles for Scanning Electron Microscopy by Madelaine Frazenburg from the Electron Microscopic Unit, Central Analytical Facilities, Stellenbosch University. What is scanning electron microscope? A scanning electron microscope produces images of sample by scanning it with a focus beam of electrons. The electrons interact with an atom in the sample, producing various signals that can be detected and that contain information about the sample's surface, topography, and composition. The electron beam is generally scanned in a raster scan pattern, and the beam's position is combined with the detected signal to produce an image. SEM can achieve resolution under 1 nanometer. Why use it? It is for relatively fast and reliable results. Its versatile functions, excellent spatial resolution, and the ability to analyze composition of a very small volume. What we have available at the Scanning Electron Microscope unit at Stellenbosch University is a Leo SEM, what we basically use for secondary images and CL images, a Zeiss Evo SEM, where we can do secondary plus backscatter images, plus a cryo, EDS, and WD system. A Madelaine SEM for both imaging purposes, secondary, backscatter, CL, a cold stage with an EDX and STEM detectors. On our Tygerberg campus, we have our Thermo Fisher Aprio 3D SEM. Our equipment in our lab available at Stellenbosch University, together with the different instruments. We also have a light microscope and a Zeiss Axial Imager. Comparison between light microscope and electron microscope. Optics of the electron microscope are analogs to the light microscope. Same optical formulas apply. Illumination source, lens, and the lenses consist of condenser, objective, additional magnifying lens, detection system as the eye, film, CCD, camera, except for EM uses a focus beam of electrons, not photons, for image generation. Comparing SEM and a TEM. The electron beam for a transmission electron microscope is broad and static beams. For a scanning electron microscope, the beam is focused to a fine point. Sample is scanned line by line, or rectangle by rectangle. Voltages needed for a transmission electron microscope is from 60 to 300 volts, whereas by a scanning electron microscope, the accelerating voltage much lower, not necessary to penetrate the specimen. Specimen must be very thin for a TEM. For SEM, wide range of specimens allowed simplifies sample preparation. Imaging. For transmission, electrons must pass through and be transmitted by the specimen. Scanning electron microscope information needed is collected near the surface of the specimen. Image rendering. Transmitted electrons are collectively focused by the objective lens and magnified to create a real image for transmission electron microscope. Whereas by a scanning electron microscope, the beam is scanned along the surface of the sample to build up an image. We can also compare the light microscope with a scanning electron microscope according to the source of illumination. Light is replaced by an electron gun built into the column. The lens type. For a light microscope, it's the glass lenses, and for electron microscope, we use electromagnetic lenses. Magnification method. For a light microscope, magnification is changed by moving the lens. In the EM, the focal length is charged by changing the current through the lens coil. In a light microscope, you use the eyepiece or ocular. In an EM, the fluorescent screen or digital camera. Use a vacuum no vacuum in a light microscope, but in an EM, the entire electron path from gun to camera must be under vacuum. The SEM is composed of several primary operational systems. For instance, the vacuum, A vacuum, typically 10 to minus 5 to 10 to minus 11 torr, is required when using an electron microbeam because electrons will quickly disperse or scatter due to collision with other molecules. A vacuum, typically 10 to minus 5 up to 10 to minus 11 torr, is required when using an electron beam because electrons will quickly disperse or scatter due to collisions with other molecules. The electron gun generates the primary electron beam at the top of the column. There are two types of beam emission to excite the electrons off the filament. First, the thermal emission type. Electrons are extracted from heated filaments by applying high electric potential between filament and anode. Tungsten filament that can be operated at a lower vacuum, 10 to minus 4 torr, with short lifetime, plus minus 100 hours, and low electron emission inadequate for high resolution SEM. Lab 6 filament that have a higher electron emission, better resolution, and a longer lifetime, plus minus 200 hours, but with high cost and higher vacuum, 10 to minus 6 torr, is needed. With a field emission, we have a cold field emission and has a sharp single crystal tip mounted on a hairpin filament and a strong electric field of 10 to minus 7 volume per meter is applied between tip and aperture anode to induce electron tunneling through a barrier at ambient temperature. The advantages are cool emission, much narrow beam width, plus approximately 5 nanometers, and longer filament lifetime. A high vacuum is needed, up to about 10 to minus 11 torr, to keep tip clean. A Scotty emission secondary has similar setup as the cold field emission, with a tip coated with zirconium and heated to facilitate electron emission and tip clean. Scotty emission has a higher source of stability and low beam noise, high electron yields comparing to the cold field emission. Electron beam manipulation. This system consists of electromagnetic lenses and cores located in the microscope column and control the size, shape, and position of the electron beam on the specimen surface. The electromagnetic lenses are formed by passing electric current through copper wires to induce magnetic field. Condenser lens performs a spot size control by converging the cone of the electron beam to a spot below it, before the cone flares out again and is converged back again by the objective lens and down onto the sample. The beam passes through two sets of magnetic scanning coils for beam scanning in both X and Y directions. The magnification is controlled by modulating scan area. The smaller area, the larger magnification. The objective lens focuses the beam onto the spot on the sample. This is necessary to have an image in a proper focus. Interaction between primary electron beam and sample generates a multitude of signal types: backscatter scattering electrons, secondary electrons, X-ray orbit electrons, and chemiluminescence. The topographical information is obtained through backscatter and secondary signals. Secondary detector magnetically attracts emitted secondary electrons by a low positive voltage applied to a ring around the detector. Upon entering the ring, the secondary electron is attracted and accelerated by a high positive voltage, plus minus 10 keV, on the scintillator. The secondary electron hits the scintillator, causing photons to be emitted. Photons emitted from scintillator travel down the light pipe, hitting the photomultiplier. Secondary imaging, being more surface sensitive due to short electron escape depth, plus minus 10 nanometers, has higher spatial resolution and provides mainly topographical information. The basket detector is similar to the secondary detector, but without positive voltages applied. To maximize the detection of the backscatter signals, the detector is positioned as close to the primary beam as possible without interfering with the primary beam. Backscatter imaging has a lower spatial resolution due to longer electron escape length. However, as in backscatter intensity is proportional to the mean atomic number of the atoms, the backscatter imaging provides information on variations in sample composition. How do we get an image? Simply said, electrons in, electrons out, or X-rays out. In brief, we shoot high energy electrons and analyze the outcoming electrons or X-rays. Image formation uses a scanning principle. Deflection coils are used to steer the beam. Primary electrons scan across the specimen in a raster pattern, and an image of this area can be formed by collecting electrons from each point on the specimen. Pixel intensity is proportional to signal received. The secondary electron signal is amplified and represented as a secondary electron image of the specimen on a digital monitor. In raster scanning, the image is generated serially, point by point. The monitor and scanning deflectors coils are synchronized. Signals from the sample get detected by different types of detectors. For instance, we get secondary electrons, backscatter electrons, orb electrons, cathodoluminescence, and X-rays that we use for ED and WDS. Types of electrons and beam interaction. Volume of interactions versus accelerating voltage. The blue tracks in the image show primary electrons, trajectories that terminate in the sample. The red tracks in the image are primary electrons that ultimately escape from the sample as backscatter electrons. Backscatter electrons can exit the sample surface from the beam spot, potentially creating secondary type 2 that degrade the resolution of the secondary signal. Electron beam can penetrate a sample depth based on the different kVs we applied. With a 25 kV, you can penetrate a sample by 5 microns. 15 kV, 2.5 microns. A 10 kV sample, 1.3 micron. And a 5 kV, we can penetrate very close to the surface, a 0.4 micron that we normally use for imaging. Interaction volume increases with increasing accelerating voltage and decreases with increasing atomic number. If we can compare a scanning electron microscope with a SEM, we get the different types of electron guns. Firstly, thermionic emitters use electrical current to heat up a filament, and the heat overcomes the work function of the filament material. The electrons can escape from the material itself. A field emission gun does not heat a filament. The emission is reached by placing the filament in a huge electrical potential gradient. With field emission guns, we get a smaller spot and higher current densities compared to thermionic guns. Vacuum requires are higher for a field emission gun. For samples that we can load in a scanning electron microscope, we need to consider the size of that can fit into a chamber. It's very important that we introduce only dry samples into a scanning electron microscope chamber and a sample that is conductive. Most of the time, an aluminium stub gets used with a double-sided carbon tape or adhesive or electrodag paint to place a sample and to adhere to keep it in place when the beam is resting over it. On your left-hand side, we can see that we can image samples from 1 centimeter down to 0.1 nanometer scale and affect them, but you are limited with the different filament types. That a normal tungsten filament, you can go down to a micro scale, and with a tungsten crystal, you can image down to 0.1 nanometer scale. Different imaging detectors. In our Madelaine SEM, we have in-lens secondary detector, a backscatter detector, CL detector, and a SEM detector. How can we perfect an image? By signal processing. It should be noted that signal processing can greatly change the appearance of an image relative to that which might usually be expected. Normally, however, it is considered routine to adjust the image quality using the contrast and brightness, contrast control, and black level control to give a crisp appearance to a secondary image. Accelerating voltage versus specimen type. In theory, an increase in accelerating voltage will result in a higher signal or lower noise in the final image or micrograph. But this situation is not so simple. There are some disadvantages. For example, reduction in structural details of the specimen surface in secondary mode, increased electron buildup in the insulating samples, causing charging artifacts, increased heating, and the possibility of specimen damage. With a higher accelerating voltage, the electron beam penetration is greater and the interaction volume is larger. Therefore, the spatial resolution micrographs created from those signals will be reduced. The number of backscattered electrons will increase. For secondary electron imaging at typical voltages, say about 15 keV, backscatters can enter the secondary electron detector and degrade resolution. If we look at our table, a working guide to a selection of appropriate accelerating voltage. keV range against application. So from 1 to 5 keV we use for a delicate and uncoated specimen. For keV from 5 to 10 is mainly used for coated biological samples, and the keV for 10 to 30 keV is mainly used for physical science samples. The size of cross-sectional diameter that the cone of the beam makes on the surface of the sample affects number 1, the resolution of the image, 2, the number of electrons generated, therefore the graininess of the image. At low magnifications, we use a larger spot size than at a higher magnification. The size of the spot affects resolution. The beam scans across the sample but is actually made up of moments when it dwells on the sample. Each moment or spot, as we see here, generates signal that makes up the final image. Images taken at the same magnification, keV, and working distances, but using different spot sizes show different effects. The difference in blurriness resolution is easily seen across the series. The spot size on the far left side is 60 and the spot size on the far right is 17. The way spot size is reported depends on the make of the machine used. The image is of a cross-section through a carbon fiber. Note the round profiles embedded in the polymer. Scan rate and signal-to-noise ratio. The slower scan rate allows more electrons to be collected at each point along the line of the beam scan. This produces a better quality image. The image quality of the SEM is limited by the spot size, and the ratio of the signal produced by the electron beam to the noise imparted by the electronics of the instrument in the displaying of the signal. Noise pulses are derived from such sources as beam brightness, condenser lens settings, spot size, and secondary detector gain, and may impart as salt and pepper graininess appearance on the image. When the SEM is set up for high resolution imaging, it will often have a low signal to noise ratio and appear grainy. So the faster the scan speed, the more grainy your image, and the slower your scan speed, the more smooth is your image, or the less grainy your image. Working distance Z control is used to either raise or lower the specimen. The working distance impacts on the depth of field and the resolution of the sample image. As the working distance is increased, the beam divergence angle is decreased, which provides a greater depth of field. The trade-off for an increased working distance that the electron beam must travel greater distance from the gun and therefore has a larger spot size on the specimen. Both images have different depths of field, although they both show very good quality resolution in the lower and at the higher end of this image. Sample height or working distance refers to the distance between the bottom of the SEM column and the top of the sample. Within the sample chamber, the sample stage can be wound up closer to the end of the column, a short working distance, or drop down lower, a long working distance. The shorter the working distance, the smaller diameter of the beam is at the sample surface. So, when possible, the working distance is kept at 10 mm or smaller for high resolution imaging. So the smaller your working distance, the better or the higher or the better quality resolution image you will generate. Charging is produced by build-up of electrons in the sample and the uncontrolled discharge, and can produce unwanted artifacts, particularly in secondary electron images. When the number of incident electrons is greater than the number of electrons escaping from the specimen's surface, then a negative charge builds up at this point where the beam hits the sample. The negative charge arises from electrons, ions, irradiation on a non-conductor sample is known as the charging effect or specimen charging. The negative charge will also reduce the landing energy of the incident electrons, and it would increase the field between the surface and the secondary electron detector. A sample preparation solution to such a problem can be recoated the sample with a thicker layer of gold. As we can see the build up in the three different images, some show a brighter area and in some areas is less brighter surfaces. In the SEM, the magnification is the ratio of the area scanned on the sample to the output device. The smaller the area scanned, the higher the magnification and vice versa. Where do the signals come from? The diameter of interaction volume is larger than the electron spot. Resolution is poorer than the size of the electron spot. Secondary electrons generated from the collision between the incoming electrons and the loosely bounded outer electrons. Low energy of 10 to 50 eV, electron volts, only secondary generated close to the surface escape, which give you topographic information. Number of secondary is greater than the number of the incoming electrons. We differentiate between a secondary 1 and a secondary 2. Secondary 1 versus secondary 2. Secondary 1, the secondary electrons that are generated by the incoming electron beam as they enter the surface. High resolution signal with the resolution which is only limited by the electron beam diameter. The secondary electrons that are generated by the backscattered electrons that have returned to the surface after several inelastic scattering events. These secondary 2 electrons come from a surface area that is bigger than the spot from the incoming electrons. The resolution is poorer than that of the secondary 2 electrons exclusively. Factors that affect secondary emission: work function of the surface, if it's uneven, beam energy and beam current, the atomic number. More secondary electrons are created with increasing Z. The Z dependence is more pronounced at the lower beam energies. By placing the secondary electron detector inside the lens, mainly secondary 1R detectors, resolution of 1 nanometer is possible. Here we can see different types of in-lens and secondary 2 images. Backscattered electrons. A fraction of the incident electrons is retarded by the electromagnetic field of the nucleus, and if the scattering angle is greater than 180 degrees, the electrons can escape from the surface. We differentiate between backscatter 1 and backscatter 2. X-rays are not electrons. Each element has a fingerprint X-ray signal, poorer spatial resolution than backscatter and secondary. Relatively few X-ray signals are emitted and the detector is inefficient, therefore relatively long signal collecting times are needed. Cathioluminescence, mainly minerals emitted radiation, photons, referred to as luminescence, when bombarded with an energy source. Source is of high energy electrons, where the cathode is the source of the electrons, cathioluminescence. Emission of characteristic visible as UV light. Getting started at the EM unit, you can contact me, Madelaine Frazenburg, and you can then explore also our website, or you can register to become a user as a SAF user. Thank you for your time.